Okay, welcome back. We are now going to study variogram model fitting. So, the idea in variogram model fitting is to search for a valid variogram that is closest to the spatial dependence in a given sample data set. So, what we have to start with is really a given sample data set. So, let us do that. So, we represent our sample data as a vector z, which is equal to z at location S1, z at location S2, z at location S3, keep going till location z at location Sn, right, where location points S1, S2 till Sn are my spatial entities at which I have sampled the data. Everywhere else I have not sampled the data. Okay. So, now so this vector is all these values contained in this in row vector transposed. That means that z by itself is a column vector. So, it is a vector of size n by 1, that is to say that z is really looks like an Excel and a column of in an Excel sheet where you have values spread out as along the cells in a column, right. So, this is just to give you an idea of vector notation, which is not really very difficult, right. So, next let us consider the family of isotropic linear variograms, right. So, we are working with isotropic linear variograms. That means that my lag vector h is diverse only to the extent of distance that it represents. In each direction, the data that I am working with is going to exhibit the same spatial properties, right. If the data were anisotropic, then direction too would have become as important as distance, right. So, then if I were to do a north south lag of 100 meters, it will not give me the same spatial dependent structure as the east west lag of 100 meters, right. In our case, when we study isotropic, direction really becomes a uniform representation of the process in all directions, right. So, direction is not really the entity of lag, it is really just a distance, it is just to make my own life easier and also to restrict ourselves to the scope of this course, right. We are not working with an anisotropic data so far as this course is concerned. Okay. So, we have seen this family previously, it is called 2 gamma such that gamma h is equal to C 0 plus B h such that C 0 is greater than or equal to 0 and B is greater than or equal to 0. With this family of linear variograms, our aim is to choose from the above family or set of variograms the parametric model that is closest to the real world situation or that is closest to the data that we have. That is, we want the set P of 2 gamma such that 2 gamma h equals 2 gamma h and theta, right, and this theta lies in a definitive parametric space. It is just the space in which theta can move, right. Theta cannot be arbitrarily anywhere, it is supposed to be lying within a given set this capital theta. Okay. So, for the linear variogram, this theta is really a vector by itself which contains C 0 and B. And ultimately, the problem boils down to choosing parameters C 0 and B, C 0 and B such that 2 gamma h theta fits, right, fits well to the given sample data set. Okay. Now, we need to understand what does it mean, and what will it take to fit a good, model to the given data set, right. So, for fitting the best model, on a variogram cloud, remember we always have this cloud from the experimental variogram, right, and we are trying to fit a model onto it. We will need an assumption on the distribution of spatial data. Right. So, as statisticians, we view the world as a sequence of random processes. As spatial statisticians, we view the world as a sequence of random processes in space, right. So, we need an assumption on the distribution, right. I mean, so random processes will have specific distributions and we need to specify a distribution. So, what we need is for these values z, we need to be able to specify a CDF from which these values are being drawn. Not only that this CDF representation f of z will also provide us a property of how the values are connected in space, right, in a modeled sense. Usually, right, f z is assumed to be Gaussian. What does it mean when I say f is assumed to be Gaussian? That is, it is usually assumed to be normally distributed, a random variable or a random function. Why? Well, because as we will see, it allows us to specify a nugget effect, right. We have seen that the nugget effect is usually considered white noise, and that is why a Gaussian assumption on f of z will allow us to specify a nugget effect, which is then very important in order to estimate an unbiased variogram, which then allows us to estimate an unbiased variogram. Okay. And the second thing that we will be needing in order to fit this best model is a goodness of fit criteria. I need a judgment device in order to figure out what is a best model or what is a better model relative to an alternative, right. So, we need a criteria. In case of regressions, if you I hope most of you have seen a regression model. Even if you have not, I am sure you must be aware of this statistic called R squared. R squared is a goodness of fit criteria, right. There are multiple alternative goodness of fit criteria out there. We will need such a criteria in order to figure out what is the best model variogram for the real world. Okay. So, we will now go over each algorithm that we had introduced. So, the first one was called as the maximum likelihood estimation. Okay. Maximum likelihood estimation relies crucially on the Gaussian assumption. On f of z. Okay. Now, the process of maximum likelihood estimation aims to recover a parametric variogram model by exploiting the variance covariance matrix of data in a spatial domain, right. So, let us write that down. The process of MLE, which is an acronym for maximum likelihood estimation. The process of MLE aims to exploit or use recover a variance covariance matrix or structure of a spatial data set in order to provide an estimate of the variogram. Okay. Now, to see this process, let us begin with a case where the data are independent. So, with a no spatial dependence case. Right. So, we will start with a case which is simplistic, right, which will have no spatial dependence. We will conduct MLE on it, and then we will introduce spatial dependence to the structure, and then we will see how MLE will work in order to provide me an estimate of the parameter vector theta, and hence a parameter model, variogram model, 2 gamma h theta. Okay. So, we are given a sequence of data. What is the sequence of data? It is Z1, Z2, Z3, keep going all the way till Zn. Okay. We define this as a vector Z. Okay. Again, the data vector is a column vector. So, it is a n by 1 vector, right. So, it is like you can imagine an Excel sheet and a column of cells where these data are recorded. Okay. Now, remember, we are given a sequence of data. We have said that in order to do any analysis in maximum likelihood, we need the Gaussian assumption, right. So, it is the first crucial assumption that I must take, that is, we are going to say Z I are IID, that is independently and identically distributed as normal mu comma sigma squared. So, they are normally distributed with mean mu and variance sigma squared, right. Now, in this formulation, I am going to do a little aside. I could set, if I set mu as let us say xi beta, where xi is a vector of size 1 by k and beta is a vector of parameter k by 1, right. That is, all I am writing here is beta 1 x 1 I plus beta 2 x 2 I plus beta k x k I. Then I am basically providing a setting which looks like a regression model, right. So, then this setting would resemble the MLE or the maximum likelihood estimation of the following regression model, that is Zi equals beta 1 x 1 I, beta 2 x 2 I, beta 3 x 3 I plus ui. Okay. So, in this regression model I have a systemic portion, a systemic component. The systemic component is the one which can provide you a systematic, how is the variation in Zi explained by systematic factors x 1 till x k. If Zi were groundwater data, x 1 might be rainfall, x 2 might be the amount of discharge, x 3 might be something like industrial demand, x 4 might be something like policy, groundwater management policy, which restricts the let us say number of electricity hours on a farm which draws groundwater, and so on and so forth. It could be price of water, it could be alternative sources of water, it could be aquifer properties, and so on and so forth. These are observed physical and social and economic factors around us that can explain how groundwater values would actually evolve over time or over space, right. These systemic components provide me a portion of the variation in Zi that I as an analyst can explain by choosing xi's and then estimating betas in a linear coefficient form attached to each xi, right. However, groundwater values are likely to be more complex in the way they evolve over space, that is how they change by I. The portion of variation in Zi's over space that I cannot explain is captured in this residual or error component. This is the component of groundwater variation that I as an analyst cannot explain through this model, right. The model is linear, it is restrictive, it could be highly nonlinear, right. One of the xi's xk's could be squared, or they could be, I could include them in square root. I could even multiply x2 and x3 and include that as a separate variable. I do not do any of that, it is a simplistic model. Again, it is a model, it is a imperfect representation of the real world, but it provides me with a lot of information which is generalizable across space, right. Because it is an imperfect representation, there is a component which remains as an error component, and rather it is a random error component. Okay. If I were to, instead of mu, if I were to say Zi is IID n xi beta, I am basically talking about a regression model, right. So, we will work with the sequence such that its mean is just mu, but you should be aware that we could just simply extend this formulation to a regression framework. Okay. So, given coming back to our problem that Zi is IID n mu comma sigma squared, the likelihood or probability, the likelihood of observing Zi in the given sample is given as f, that is the PDF of Zi, this is the continuous PDF representation, and the parameters mu and sigma squared. This f value is given as 1 over square root 2 pi sigma squared exponential minus half Zi minus mu over sigma the whole squared. The right hand side mathematical formulation comes from the specification of a normal distribution. It represents a normal distribution. But given the value of Zi, once I know my Zi value, I can actually back out the probability or the propensity of observing this value in my sample. What is the a chance that I will observe, let us say Zi equals 5 given parameters mu and sigma squared, right. This functional form will provide me that chance of observing each Zi. Okay. Now, after having learnt the probability of observing a particular Zi, I want to now figure out the likelihood or probability of observing the entire sample. Okay. So, if I have the probability of observing one Zi, one of the Zi's, what is the probability of observing all the Zi's at once, right? Basically the sequence Z1, Z2 through Zn. Remember, each Zi, that is Z1, Z2 is simply a random draw from this normal distribution. So, the fact that I have a particular sequence of n values itself is a instance of chance, right, and I am trying to figure out what is the probability of observing the sample itself given that each Zi is IID normal mu comma sigma squared. So, what I am after is f of Z1, Z2, Z3 all the way till Zn. I am looking for the probability of this sequence of data given mu and sigma squared, right. Remember, I had said that these z values put in a column vector can be defined as a vector z of size n by 1. This z is going to be distributed according to a multivariate normal of size mu and sigma squared. Now, because I have a z vector of different zi's, each zi has an attached mean mu to it. So, n by 1 vector of z's will have a mean n by 1 attached to it. For variance, a n by 1 vector will have a variance covariance matrix of size n by n, right. So, then sigma squared, which is a scalar, is not enough. I need an identity matrix to be attached to it, which is, let us say, sigma squared I n. I should be working with smaller n values. So, let me just make that correction in a minute. N by 1, n by 1, and then n by n by multiplying sigma squared by a identity matrix. By doing that, what I have really done is, what I am saying is that the column vector Z1, Z2, Z3 all the way to Zn is distributed normal according to with a mean vector of mu, mu, mu of size n by 1 and a matrix n by n matrix having the the diagonal values being sigma squared and off diagonal values being 0, basically suggesting that the covariance between any of the zi's is 0, which makes sense because we are working with no spatial dependence, no dependence in data. We are working with identically and independently observed data. So, off diagonal elements will be 0. When we introduce spatial dependence to the data, we are going to change the fact that the variance covariance that is the off diagonal elements of this covariance matrix is no longer going to be 0. Okay. So, I have a n by 1 vector normally distributed IID with n by 1 mean vector and a n by n variance covariance matrix, where the off diagonal elements are 0 because I am working with the IID, which is independently drawn distributions from the same which is the same distribution normal with the same mean and a variance sigma squared across all zi's. Now, when I write this, when I get back to my problem that I am trying to solve, is that I have to figure out what is the, I know f z I want f of z vector, which is all the values in my data sequence. This is going to be given as mu comma sigma squared I n is equal to f of observing the first z1 times observing z1 conditional on observing z2 conditional on the fact that I have observed z1 times I have the probability of observing z3 conditional on the fact that I have observed z2 and z1, keep going all the way till observing zn conditional on the fact that I have observed zn minus 1, zn minus 2 all the way till z1. Okay. Now, the fact that we have an IID assumption, so given the IID assumption, what happens is that the conditional density is equal to the marginal density. That is, the probability of observing Z2 does not depend on what Z1 was, or the probability of observing Zn does not depend on what happened earlier when we draw Z1, Z2 all the way till Zn minus 1. It is independent of what is happening before or after it. That is not going to be the case if we had spatial dependence in data. But with the IID assumption, we can write f of z mu comma sigma squared I n equals f of z1 times f of z2 times f of z3 times f of z4 times keep going till f of zn. That is, we have a multiplicative representation, I goes from 1 to n f of zi, which is to say we have multiplication of I goes from 1 to n 1 over square root 2 pi sigma squared exponential minus half z I minus mu over sigma the whole squared. And this f of z I am sourcing directly from what I have presented earlier. If I were to solve this, I am simply going to get I am going to multiply each component n times. So, I am going to get 1 over 2 pi sigma square to the power n over 2 times exponential. So, you have exponentials e to the power this stuff being multiplied for each z I. So, I am going to write this is going to be minus half summation I goes 1 to n z I minus mu by sigma the whole squared. Let us take it to the next page. So, we have the likelihood of observing our sample given z I our IID normal 0 comma sigma squared being given as f of z vector, which is a n by 1 vector given mu and sigma squared equal to 1 over 2 pi sigma squared to the power n by 2 exponential summation minus half I equals 1 to n z I minus mu sigma the whole squared. All right. Now, with that we take a log of this, and that is called as the log likelihood. So, the log likelihood of observing the given sample. So, I can call this f, I can define this as L of mu and sigma squared, the two parameters that I am after. Log likelihood of this is going to be ln L mu comma sigma squared equals minus n by 2 log of 2 pi minus n by 2 log of sigma squared minus 1 over 2 sigma squared summation I equals 1 to n z I minus mu the whole squared. Now, my objective is to maximize. So, my algorithm is called maximum likelihood estimation. I have the likelihood of observing the sample. The next step is to maximize the likelihood of observing this sample. So I am just going by the nomenclature, I am going to maximize this, and when I maximize this, my choice variables are mu and sigma squared. So, these are my variables that I can choose. I have a degree of freedom what mu and sigma squared values could be, right. So, I could choose mu and sigma squared such that the likelihood of observing this given sample, the sequence Z1 till Zn is maximized given that Zi's are IID normally distributed with parameters mu and sigma squared. So, this is an optimization problem, and when we face such an optimization problem, we write our first order conditions. Okay. So, our first order conditions will be del ln L by del mu, that is the first differential, partial differential by our first choice variable. This will be set equal to 0, then del ln L by del sigma squared, that is our second choice variable, this will be set equal to 0. Overall, I have two equations and two unknowns. Okay. So, I can solve this. When I actually solve this, we will find that mu hat ml, that is the maximum likelihood estimator for mu, will come out to be z bar, which is nothing but the sample mean of all the zi's. Whereas, sigma hat squared ml, which is where the hat means it is a data driven estimate and ml means it is a maximum likelihood data driven estimate. That is going to come out to be summation I equals 1 to n z I minus mu hat ml, which is nothing but the z bar value divided by n. Okay. Now, these are my maximum likelihood estimators, without spatial dependence. Okay. So, as a next step, as a next natural step, what we are going to do is that we are going to add spatial dependence to these data and see what happens and how these parameter estimates change, what changes when we add spatial dependence to the data. Clearly, the first thing that is going to happen is that I am not going to have sigma squared in as my variance covariance matrix, right. My variance covariance matrix will be more complicated because my off diagonal elements are going to be non-zero. So, the first change that you are going to observe is at the off diagonal elements of the variance covariance matrix of this vector. Okay. So, let us move forward and do that.